Okay, so here we have to find radius of curvature at point P on a curve y equal to fx. So this is actually a two-dimensional curve. So this is right, y is equal to fx. So let's choose a point P here. Radius of curvature at point P. What is the meaning of this is, say, choose a very close point P dash. P dash is very close to P, so that P is having coordinates x comma y, and P dash is having coordinates x plus dx comma y plus dy. So at these 2 points, if you draw perpendiculars or normals to the curve, then they will meet at the center of curvature C, and thus you can find out radius of curvature R. Okay, so so here you know that we can draw the tangents at point P. So tangent at point P makes angle theta with the positive direction of x-axis, and tangent at point P dash, that makes angle theta plus d theta with the positive direction of x-axis. So the angle between the two red lines, that means the angle between the two tangents, it's obviously d theta. So angle between tangents is angle between the normals. So angle between the two green lines in the figure is d theta. So now this P to P dash, that distance. Now we can see a center C and an arc of radius R. So arc of radius R and arc of length P dash. So here you can write R multiplied by d theta is the small length P dash. Right, now this P dash you can write P dash is so small, it's almost a straight line connecting P to P dash, right? So this P dash, almost, if it's a straight line connecting P to P dash, so the sides of the triangle, this little triangle dx and dy. So it's root over of dx square plus dy square. So that's a good enough approximation, because as it's very small, P dash is very small. Okay. Now, so and again this d theta. So tan theta is dy by dx. Tan theta is nothing but the slope of the tangent. So if you differentiate it with respect to x square theta times d theta by dx is equal to d2y dx2, because you will get d theta by dx here. So 1 plus tan square theta. So tan square theta I can write dy dx square times d theta by dx equal to d2y dx2. Okay, let's keep it aside as equation 1. Now from these two lines, first and second line, we'll get here that r is P dash by d theta. So we will bring out dx out of the bracket, so it becomes 1 plus square root of dy dx square. Now this, so d theta by, so and let's name this equation 2. Now you combine 1 and 2. So from 1 and 2, I'll write the value of r as, now dx by d theta is see, from 1, dx by d theta is 1 plus dy dx square divided by d2y dx2 multiplied by square root of 1 plus dy dx square. So that means, that implies r becomes what? 1 plus dy dx square to the power 3 by 2 divided by d2y dx2. So this is a formula for radius of curvature. It's worth remembering. Now I'll show a very simple example. So this is the problem we are going to solve, that a projectile is fired at a speed u making angle theta with ground. Find radius of curvature of the path at the highest point. Radius of curvature at the highest point of the path. So that's the path, it's thrown at a certain angle u making angle theta with ground. Now what we'll do is that we'll write the equation of the path. So if you recall, then y equal to x tan theta minus gx square by 2 u square. I have cos square theta. Okay. Now we will use the formula of radius of curvature. Now dy dx is tan theta minus 2gx by 2 u square cos square theta. This 2 will cancel out. So that's tan theta minus gx by u square cos square theta. Now this d2y dx2 is minus g by u square cos square theta. Now the formula of radius of curvature was r is 1 plus dy dx squared to the power 3 by 2 divided by d2y dx2. And remember, it was mod of that, right? It was mod of that, because the sign doesn't matter. We are concerned with at the point P. It's part of a large circle, so the radius of that circle, so the sign doesn't matter. So that's radius of curvature for us. Okay, so at the highest point, as you know, the particle is going like this flat, so dy dx is obviously equal to 0. So therefore radius of curvature is 1 plus dy dx. So numerator you have 1, so d1 upon d2y dx2 is u square cos square theta divided by g. So that is the answer, and this is the radius of curvature at the highest point. Now let's recall a different method we have used from that tangential, that normal acceleration viewpoint. So for any path, radius of curvature is given by square of the speed divided by the normal acceleration. That means if it has a velocity v, so it may have a tangential acceleration and a normal acceleration. So this part of the curve is part of a large circle having radius r. That is the radius of curvature given by this, and this c is center of curvature. So v square by the normal component of the acceleration. So at the highest point of the projectile, the speed is equal to u cos theta, because it was thrown at u making angle theta with the ground. The horizontal component will, and that at the highest point the vertical component is 0, and the acceleration of the particle is always g, this point also. And so this here g is perpendicular to v, so g is equal to an. So at the highest point we can calculate radius of curvature as v square by an, that is u cos theta whole square, divided by an is g, so u square cos square theta by g.